Hello, good morning. So this video is about the development and evolution of the plate tectonic theory. So recall that the plate tectonic theory, the modern plate tectonic theory, is actually a conglomeration and the combination of all the ideas that were put forward before it, namely continental drift theory, seafloor spreading theory, the concept of convection currents, and the internal structure of the Earth, right? The layers of the Earth. So here we want to discuss what are the contributions of each. Okay, so number one, the continental drift theory started the whole idea that continents move around the planet. It is the thing that started it all, because if not for the continental drift theory, then we would have thought what people have always thought, that that the surface of the earth is unchanging. So this earth is very big, very huge, so how could it be changing? It should be the same before ways millions of years in the past. And then seafloor spreading theory provided an explanation why the continents move. Because remember, in continental drift theory, the weakness was it doesn't explain why the continents move. It had a lot of evidence supporting that the continents did drift, but there was no explanation why they would drift. So the seafloor spreading theory provided an explanation by looking at magma coming out in ocean ridges. But again, it's a cascade of questions. If it's the magma that comes out of ocean ridges that causes the continents to drift, then what causes the magma to rise out, to rise up in from the mantle? So now we go into the concept of convection currents. So convection currents um, simply suggest that the movement of these structures at the surface of the earth is caused by forces deep within the earth, and um, this kind of catalyzed the process, or the investigation into what really is the structure of the earth. So when we discovered earthquakes, how to record earthquakes, P waves, S waves, and we developed techniques in physics, for example, we tried to find out what the internal structure of the earth, and the internal structure actually provides a setting to why these things happen. So for example, why would the continents drift? Well, because the lithosphere of the earth, which is a concept in the internal structure of the earth, is fragmented, right? So these are the contributions of each of this. But more importantly, we want to kind of track what are the changes in the concepts as these develops, as these concepts were assimilated and transformed into the modern plate tectonic theory. So before continental drift theory, people thought the Earth is unchanging, its surface features are unchanging, continents and oceans stay the same over time. But with Alfred Wegener and the other scientists who noticed the jigsaw fit of the puzzles that pioneered it, but it was Alfred Wegener who really created the theory. He thought that the Earth's features are changing, specifically the continents. He thought the continents are moving and it's just plowing through the unmoving ocean. So he thought continents are moving, but oceans are not moving. Right? By the time we come to seafloor spreading theory asserts that no, Wegener, you're wrong. The oceans are actually not unmoving. There are ocean ridges and subduction zones, and it's actually the seafloor that is causing the movement. There's actually magma that comes out of oceanic ridges that pushes the seafloor to move. So again, the oceans are moving, and because the seafloor is connected to the continents, so as the seafloor moves, also the continents move. So therefore, it provided an explanation for why the continental drift theory, why the continents would move, right? And then convection currents. Now, Seafloor spreading theory only says that there's an upward motion of magma in the ridges, but what causes the upward motion? So scientists, referred to an old concept in thermodynamics, heat transfer, which is convection currents. So we thought that the mantle has fluid-like properties, and because it's a fluid-like materials, then convection applies to it, wherein when something is heated at the bottom, the materials kind of move up, and then as they cool down, they move down, and you create this cycle, circulation of materials, of fluid materials. Okay? So magma comes out of ocean ridges because the convection currents in the mantle push it upwards. Okay, so this is now the explanation for why the magma comes out of oceanic ridges. And then the sidewards movement of the convection current also affects the drifting of the continents and spreading of the seafloor, not just the upward motion of the magma in ridges. Because in seafloor spreading theory, they thought when there is a crack, between the oceanic plates, when magma comes out of it, just of the sheer upwards force, the two parts of the plates are moved sidewards. Now with convection currents, because remember, convection currents are circular, right? Convection currents are circular patterns of circulation in the magma materials. Now scientists are thinking, aside from the magma coming out and pushing the ridge, because of the circulation, the current actually drags. So you see, it drags the mantle, the lithosphere sidewards. So there's an additional concept. Instead of just magma coming out pushing the two to the sides, the magma comes out and then moves to the side as it sinks down to the bottom. So therefore, as it does this sideward movement, it also kind of drags the mantle sidewards. And then because of these things, for example here, convection currents, for the convection currents to work, the mantle materials must be fluid-like. So that contributed to some of the postulates of internal structure of the Earth. For example, we now know that the asthenosphere, at least of the mantle, is fluid-like. There is even a debate that even the mesosphere is also fluid-like, or at least a superfluid. So it's a fluid in the macro state. It's a fluid, but not in the atomic level, but in the bigger structure state. Okay, I'm sorry, this is something that is quite advanced for your level, but it's like that. So with the internal structure of the Earth, we now thought that there's a compositional and mechanical layers, and you have layers like crust, mantle, core. You have layers like lithosphere, which is made of the crust and the uppermost mantle. So take note that before, scientists thought that it's the ocean floor is simply connected to the continents, and therefore when the ocean floor moves, the continent simply is pushed also because of the movement of the oceans. Now, because of what we know about the internal structure of the Earth, we now know that there is a lithosphere. And the lithosphere is the crust, which includes the ocean floor, and the continents, the land masses, which is composed of continental crust. And both of those two types of crust are on the same segment that we call a lithospheric plate. So now it's not that the ocean floor moves, therefore pushing the continents. It's more likely that it's the segment of the lithosphere that moves. Obviously, because the lithosphere contains the ocean floor and the continental plate. Then, when the lithospheric plate moves, the whole thing moves, including the oceans and the continental crust. But that's sort of a gradual improvement of the concepts until finally we have this plate tectonic theory. It says that the Earth has layers, and the upward mechanical layers is broken into segments called tectonic plates. And then the heat in the core creates hot spots. So the heat hits up the materials in the mantle. So therefore, the materials in the mantle rises up. As it reaches the crust, it comes out of ocean ridges, but it also cools down. So as it cools down, they sink back down, and then the heating again restarts. Okay, and that because of these movements, tectonic plates are dragged and they are moving in different directions, so they collide, diverge, and slide past each other. And because of that, they create geological formations like earthquakes, tsunamis underwater. And then, just because of thermodynamic properties of things that are hot, it's inevitable that you create hot spots, right? So spots in the mantle that are relatively hotter than the rest. Again, if you study thermodynamics, you would know that no matter how you try to heat evenly a body, there will always be spots that are hotter than the other. So that's one of the explanations for hot spots. Another minor explanation for hot spots is simply that maybe the mantle is the same temperature, but there are just simply parts of the lithosphere that are thinner than the others. That's why you have hotspots. But those are the two leading concepts, and if it comes to the votation, the first explanation would be where most scientists would agree. But it pays to know that this concept of hotspot is not yet fully explained, not yet fully explained, but those are the leading candidates for explanation. Okay? And again, you don't have to cringe and say, huh? Science has not explained that yet, even up to now. We are now into 2020. Again, science does not work like that. Science is a continuous endeavor of learning things, right? So you have to comfortable with that fact. Okay, and then because of these interactions, there's a cycle of creation and destruction of the lithosphere. So, for example, created in ocean ridges, but they are destroyed in subduction zones. And then this process is the theory that builds and rebuilds the features of the Earth, because you could create mountains, you build trenches, but when they go to subduction zone, they get destroyed. So you have this concept of building and rebuilding. And this is why it's called tectonics, because the word tectonics class is from the ancient Greek word meaning ancient Greek word tecton, which roughly translates to a carpenter, or the the verb of to build something. So plate tectonics is literally the building and rebuilding of the features of the earth because of movement of plates. That's why it's called plate tectonics. Okay, so I think that would be all for this video. I don't want this to be too long, so thank you for listening.